So what is the inverse of a matrix? So I have two matrices here, A and C. A is 2, -3, 5, -7, and C is -7, 3, -5, 2. Now, just what would happen if we multiplied A times C? So we're just going to multiply these two together. So I'm going to use the dot product method. A is 2 by 2 and C is 2 by 2. So the rows and columns match, and we're going to get a 2 by 2 matrix. So the first entry, the 1, 1 entry, is the first row of A dotted with the second or the first column of B. So I get -14 and +15. So -14, +15, that's going to be a 1. The 1, 2 entry, first row, second column, is going to be first row of A dotted with second column of B. And I get -10 and +10. That's going to be a 0. The 2, 1 entry is second row, first column, dot product. I've got +21 and -21, so that's a 0. And then for the last one, the 2, 2 entry, second row, second column, I've got +15, -14, that is a 1. So we got the 2 by 2 identity matrix. And if you were to compute C times A, you would also get the identity matrix. So when this happens, we say that these matrices are inverses of each other. So that means that C is what we would call A inverse. So we use this notation, A to the -1. And you could also say that A is C inverse because they're inverses of each other. So A times A inverse is the same as A inverse times A, and it's equal to the identity. Now, not every matrix has an inverse. To start with, the matrix has to be square, and then there's a property for the determinant that will tell you if you have an inverse. So that's what we'll do next. We're going to first start with 2 by 2 matrices. How do you find the inverse? So the inverse of a 2 by 2 matrix is 1 divided by the determinant of A times the what's called the adjoint of A. So the determinant of A is when you multiply the main diagonal entries and you multiply the other diagonal entries and you subtract them. So for this matrix, the determinant of A is 3 times 6 minus 5 times 4. They have to be subtracted in this order. The main diagonal product goes first, the other diagonal product goes second, and this is 18 minus 20, so we get -2. So right off the bat, we know that we're going to divide -2 when we do our inverse. So this tells you, when would this fail? If you calculated the determinant and got 0, then you couldn't divide by the determinant to get the inverse. That would be an indication that the inverse does not exist. Okay, so not all matrices have inverses, but if you get a determinant that's equal to 0, then you know that that inverse doesn't exist. If it's anything else other than 0, then you can find the inverse. Now the adjoint is a matrix. And you switch the entries in the main diagonal, and you change the signs of the off diagonal, of the other diagonal. So you switch the main diagonal entries and you change the signs of the other diagonal. And we get, if I multiply by -1/2, this would be -3, this would be 5/2, +2, and -3/2. So that is the inverse. Let's just check and see if I multiply A times A inverse, do I get the identity matrix? So I'm just going to multiply these together and see if what we did was correct. So for the 1, 1 entry, I've got -9. I'm just going to write this down. -9 plus 4 times 5/2, so it would be 10. So that's going to be equal to 1. And then the next entry, I've got 6, and then 4 times -3/2, that's -6, so that's a 0. The 2, 1 entry, I got -15, and here 6 divided by 2 is 3, times 5 is +15, so I do get 0 there. And then for the 2, 2 entry, second row, second column, I've got 10, and then 6 times -3/2, that's -9, so 10 minus 9 is 1. So we do get the identity matrix. So you can use the inverse to solve a system. So if I have a system, AX equals B, and A has an inverse, then if I multiply by the inverse on both sides, and I have to do it on the left on both sides, then A inverse times A is the identity matrix. And the identity matrix times any matrix, and vectors are matrices, yeah, they just have one column. An identity times a matrix is just that matrix, or in this case, the vector. So we get the solution can be found just by taking the inverse of A and multiplying it times the vector B. So let's use this to solve this system. So this system is A times X equals B. And this is the same matrix that we just found the inverse for. So I have the inverse. If I just multiply the inverse times the vector B, I'll get the vector X. So I'm just going to take the inverse matrix and multiply by the vector B and see what we get. So I get -9, +14, that's 5. And here I get 15 minus 21 over 2. So 15 minus 21, that's -6. -6 divided by 2 is -3. So I get solution 5, -3. So let's plug this in and see if it works. So x1 is 5 and x2 is -3. That's 15 minus 12. That's equal to 3. This is 25 minus 18. 25 minus 18 is 7. So this is the solution. You could just say it's the vector x. So how do you find the inverse if it's not a 2 by 2 matrix? If it's 3 by 3 or bigger? Remember, the matrix has to be square to start with. So we're wanting to find a matrix A inverse such that when I multiply A times A inverse, I get the identity. So A is 3 by 3. A inverse is going to have to be 3 by 3. It's going to have 3 columns, so we'll just call this A1, A2, A3. And then the identity matrix is a 3 by 3. And remember how we multiplied matrices together. You can do it by multiplying the matrix A times the first column of the second matrix. That'll be the product column. So that tells me that this A times A1 has to be the vector 1, 0, 0. So if I solve this system, if I augment A with 1, 0, 0 and solve it, I'll get the first column of the inverse. And if I multiply A times A2, I'll get the second column of the inverse. Second column of the identity. And so if I augment A with 0, 1, 0, I will get the vector A2 when I solve the system. And if I, again, do this with A3, I will get the third column of the identity. If I augment A with 0, 0, 1 and row reduce and solve the system, I'll get A3. If the inverse exists, right? If you get a no solution, then it doesn't exist. So what we could do is actually solve all three of these systems at the same time. You know, the row operations that you would go through to row reduce A on the left will be the same for all three of these. The only thing that will change will be the last column. Those will be different for all three of these. But the operations and the order that we do the operations in will be the same. So a way to do all these at the same time would be to augment A. Instead of augmenting with each column of the identity separately, let's just augment it with all three at the same time. And we'll just do all the row operations at once. So I use a calculator and I get this row reduced matrix. So I get negative 9 halves, negative 2, 3 halves, 7, 4, negative 2, negative 3 halves, negative 1, and 1 half. So I've row reduced and I got the identity on the left. What you get on the right is the inverse, right? This is the solution to each one of these systems, right? The first column is the solution to this system. The second column is a solution to the second system, and the third column is a solution to the third system. And you put all those together and you get A inverse. So we'll say A inverse is equal to this matrix. Negative 9 halves, negative 2, 3 halves, 7, 4, negative 2, negative 3 halves, negative 1, 1 half. So in general, if you've got a 3 by 3 or larger system, augment A with the identity matrix, row reduce, And if you get the identity matrix on the left, you get the inverse on the right. Now, if you don't get the identity matrix on the left, then the inverse does not exist. Okay, you can just say there's no inverse for this matrix. Like I said, there's not going to be an inverse for every single matrix.